Can you hear me?
Yes, I can hear you. All right.
All right, so everyone can hear me, right? Just verify that you can, in fact, hear me. Okay, awesome. Then I guess let's start the review session. So this is going to be the exam 2 review. Hold on 1 second. See if this works now. Okay, it does. All right, so welcome to the exam 2 review session. So, why don't you guys tell me what you'd like to go over? All right, number 6 on homework 4. Okay, we got quite a few requests. I'm going to start with Hannah Green's number 6 on homework 4, and then I'll work through the other questions. So let's go up here, pull it up. Okay. So this is a question about which of the following are spanning sets. So let's write down some theoretical facts first about what we know about spanning sets. So here is one very useful fact. If you have a set of dim v vectors in a, hold on, in a vector space V, that are linearly independent, then they form a basis for V, and thus span V. So this is a very, very useful principle for deciding if something is a spanning set. And the reason it's a useful principle is we can easily check linear independence by either row reduction or by computing the determinant. And by this I mean the determinant of the matrix with the vectors inserted as columns. So I proved this in class, and it's a general theoretical fact, but we can in fact use it to answer this particular question. So I'm going to go through a few of these. I won't solve them all, but I'll illustrate the general approach. So let's see what we're dealing with here. Let's start with the easy one. So we'll start with A. And what I'm going to do is I'm going to take these three vectors, I'm going to assemble them into a matrix with this as the first column, this is the second, and this is the third. So my matrix A here is going to be 1, 0, 0, 0, 1, 1, and 1, 0, 1. Now, to make my life a little easier, I'm going to note that the determinant of A is equal to the determinant of A transpose. So I'm going to work with A transpose instead, just for simplicity. And so this is the vector, or the matrix 1, 0, 0, 0, 1, 1, 1, 0, 1, 0, 1. So there's a reason I did this, and that it's very easy to perform row reduction on this matrix. I mean, it's not hard with this one either, but actually they're both equally difficult, so it doesn't really matter. But I'm going to go with this one anyway. And what I'm going to do here is I'm going to set row 3 equal to row 3 minus row 1. If I do that, this is going to become the matrix 1, 1, 1. 0 here, 0 here, 0 here, 0 here, 0 here, 1 here. And so we'll call this matrix B. And then this is a type 3 row operation. So it preserves the determinant. Thus, the determinant of A transpose is equal to the determinant of B. But B here is a diagonal matrix. So it has entries like this, but computing the determinant of a matrix where that's upper triangular is very easy. All you basically do is you circle the diagonal, and you multiply all the entries along the diagonal, and that gives you the determinant. So in this case, the determinant of B turns out to be 1 times 1 times 1, so just 1. So the determinant of A is 1. This means that A is non-singular, and consequently, the columns of A are linearly independent. So, this shows that these three vectors form a basis for R3, which in particular also means they span R3. Oh, okay, I'm sorry. Sorry, I will do number 6 next. This is a review session, so I can go over as many problems as we want. Let's do 6. So take this, go over here. So, 6, let x1 through xk be linearly independent vectors in Rn, and let A be a non-singular n by n matrix. define yi to be a times xi for I equals 1 to k. Show that y1 through yk are linearly independent. Okay? So this is a proof problem. So here's how the proof goes. What we can do is we can say, suppose yi are not linearly independent. Then what we know is that if they're not linearly independent, then there is a relation C1 times y1 plus C2 times y2 plus blah, 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 Cn times yn is equal to 0. This, of course, is the same thing as C1 times a x1 plus C2 times a x2 plus blah, 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 Cn times a xn. And I guess I'm going up to k here, so I'm just going to make these n's into k's. And this equals 0. Now here's the fact I can use. Since a is non-singular, it has an inverse. Now what I can do is I can take this inverse matrix and I can multiply it by this relation. If I do that, then I'm going to get C1 A inverse times A x1 plus C2 A inverse A x2 plus blah, 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 CK A inverse A xk is equal to 0. Now we know that A inverse times A is the identity matrix. In particular, it's the n by n identity matrix. So when you multiply the vector, the xi vectors by the identity matrix, you just get them back. So this, in fact, is the same thing as C1 times x1 plus C2 times x2 plus blah, 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 ck times xk is equal to 0. So up here, we're assuming that, I didn't write it down, but we're assuming that not all ci are 0. And so this is also true down here. But then this is a contradiction. And the reason it's a contradiction is because we've assumed x1 through xk are linearly independent. So this right here, this contradicts the linear independence of the xi. And that completes the proof. And this is a proof by contradiction. Okay. I wouldn't necessarily call this a proof problem. This is more of a theory problem. It follows pretty directly just by knowing the definitions of things. There may be one or two of these on the exam to answer Drew's question. to go through this again real quick, what we're doing is we're assuming the yi are not linearly independent. This implies that there's a relation c1 times y1 plus c2 times y2 plus blah, 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 blah. ck times yk is equal to 0. Here we're just using the definition of what these yi are. And then what we're doing is we're taking this relation and we're using the fact that the matrix A is non-singular to multiply this relation through by A inverse. We do that here. And we note that A inverse times A is the identity matrix. So we can actually get rid of these matrix products, and we're left with a relation between the xi vectors. And the fact that not all the ci are 0 here implies not all the ci are 0 here, which contradicts the linear independence of the xi. Again, you could do this either as a proof by contradiction or by proving the contrapositive. When I saw it, the first way I saw it do it was by contradiction. It doesn't matter. It's fairly straightforward. All you have to note is the main idea, which is that when you have a relationship between the yi, you can go backwards using A inverse to get a relationship between the xi. Okay. So I'm going to go on and do some more questions. I'm going to go up to Savannah's question. Can we do number 6 on homework 5? So let me open homework 5. Okay. So this is a fun one. It's very geometric. So for each of the following linear operators on R2, find the matrix representation of the transformation with respect to the homogeneous coordinate system. Okay. So here's how we can think about this. Suppose we have the vector here, 1, 0. And then we want to rotate by an angle theta to a vector like this. Then the components of this vector are going to be cos theta and sine theta. So if what we want to do is we want to rotate 1, 0 by 120 degrees, well, that's basically, let's see, I'm going to do an A here first. That means I'm taking the vector 1, 0, and I'm rotating through first 90 degrees, and then an extra 30, it's like this, to get a vector like this. And what I want to do is I want to figure out what vector I put here. And so this is going to be, make it a little larger, cosine of 120 degrees and sine of 120 degrees. So I know what that is. Cosine of 120 degrees and sine of 120 degrees is actually just equal to, so cosine is going to be -1/2, and sine here is going to be square root of 3/2. So here's what I understand about my linear transformation so far. If I call it L, then L of the vector 1, 0 is this. Now I also have to figure out what L of the vector 0, 1 is. And likewise, I can kind of figure that out geometrically. So what I have to do is I have to look at the vector 0, 1, and then I go over by 90 degrees, and then I go down here by 30 degrees. And I could consult what this has to be by looking at a table of sines and cosines, but it's pretty easy to figure it out. This vector right here is basically the same as cosine of 210 degrees and sine of 210 degrees. But this right here is the same thing as, so I'm going to have negative square root of 3 over 2 right here. And down here I'm going to have negative 1/2. So I'll go over here and record that. So now that I know where it sends the vector 1, 0 and where it sends the vector 0, 1, I can conclude L is represented by the matrix A, where A is equal to negative 1/2 here, square root of 3 over 2 here, negative square root of 3 over 2 here, and negative 1/2 here. And that completes the computation of the matrix representing L here. So that's 5A. Let me finish with this problem first. So now let's look at B. Okay. So for B, let me think about this for 1 second. Okay, so for B, we're using homogeneous coordinates. So what we're going to do is we're going to understand, we're going to think of points in R2 as vectors. What are you doing? Please don't do that. That's messing with my monitor. Okay. Sorry. So what we're going to do is we're going to think of points in R2 as vectors x, y, 1. So the reason we're doing this is that we can then model this particular linear transformation by a matrix. So let's think of what it does. L of the vector 1, 0 is going to be equal to L of, well, what I do is I move it 3 units to the left, so I have to subtract 3. And then I move it 5 units up, so I add 5. Now, L cannot be modeled by a 2 by 2 matrix, but it can be modeled by a 3 by 3 one. And the reason is that L is not actually a linear transformation in the sense that we defined linear transformations in class, if we think of it as going from R2 to R2. But if we think of points in R2 as vectors, like this, then we can actually model L by a matrix. And here's how. What we do is we simply note that if we write down the matrix A, in this case, what it's going to do is it's going to take X to itself, it's going to take Y to itself,
We can't see anything on your screen.
and then it's going to subtract 3 from X, and it's going to add 5 to Y, and then it's going to leave the 1 here alone.
Professor.
Then, this matrix A represents L in the homogeneous coordinate system. So let's just verify that real quick so you guys can see how it works. So let's just verify that real quick.
The video is only showing like the top.
So if we multiply this vector by this matrix, then this is the same thing as, well, multiply this column by this row, you get X minus 3. Multiply this column by this row, you get Y plus 5. And then you multiply this column by this row, you get 1. So you can see how this exactly accomplishes what this transformation is supposed to do. I think this problem is somewhat badly written because it's claiming that L is a linear operator on R2, but it's not actually a linear operator on R2. It's only a linear operator with respect to this particular homogeneous coordinate system. And so I don't like it, and I would not assign something like Part B here on the exam, so you don't actually have to worry about it. I'll leave it alone. Alright, I'm back. It looks like it is working now. Can you all hear me? Okay, good. Then, since people don't want me to do part B again, it won't be on the exam, I'm going to skip it. I'm going to go right to part C, which is actually relevant. So, at least it's related to a kind of problem that I might ask. So we want to model the transformation L that contracts each vector by a factor of 1/3. This is actually the easiest of the three problems because, let's think about what it does. When we apply L to the vector 1, 0, it's going to take this vector, it'll contract it by 1/3, so we're just going to get the vector 1/3, 0. When we apply L to the vector 0, 1, again, it's just going to take this vector right here, contract it by 1/3, we're going to get 0, 1/3. So it's very easy to model L by a matrix. And we can say L is modeled by the matrix A equals 1/3 here, 0 here, 0 here, and 1/3 here. So C is definitely the easiest part of this problem. I'm also going to do problem 6 on homework 5. So it's this one right here. So let L be a linear operator on Rn. Suppose that L of x is equal to 0 for some x that's not equal to 0. Let A be the matrix representing L with respect to the standard basis. Show that A is singular. Okay. Well, if L of x is equal to 0, then AX is equal to 0. And what we're assuming is we're assuming that x is not equal to 0. Now, we're going to do another kind of proof by contradiction style thing. So we're going to say, suppose A is non-singular, then it has an inverse. And what we can do is we can take AX equals 0 here and we can multiply it by A inverse. And we get A inverse times AX is, well, equal to the identity matrix times X, which is equal to X, which is equal to A inverse times 0, which is equal to 0. So this implies that X is equal to 0. But this is a contradiction because we also assumed that X was not equal to 0. So these two facts contradict each other. So this is a contradiction. And we deduce that if L of x is equal to 0 for some x not equal to 0, then the associated matrix must be singular. So that completes the proof of this part of the problem. Or the entire problem, actually. So now we've done these. So someone wanted number 7 on homework 4. Actually, before that, I should talk about the Cauchy-Schwarz inequality. Will we be expected to use the Cauchy-Schwarz inequality, or is that more to show how the dot product works? That was a purely theoretical result. I will not be asking you any questions on this particular exam where you would need to use Cauchy-Schwarz. There are maybe a couple kind of problems that could show up involving it on the final exam if I decide to use it, which I don't know if I will, but no, you shouldn't expect anything about Cauchy-Schwarz for the exam tomorrow. Max Rod asks if I can do number 7 on homework 4. So let's go over here. We'll do number 7 on homework 4. Okay. This is relatively straightforward. So, let x1 through xn denote the column vectors of the matrix A The claim is that if A has linearly independent column vectors, then the null space of A should be 0. So here's what we're going to observe. Suppose AX equals 0. In other words, this is the same thing as X is an element of the null space of A. Well, what we can do is we can write X equals C1. Actually, I'm going to use a different letter here. Say Y or something, or even better, C. Call it C. So AC is equal to 0 is the same thing as C belonging to the null space of A. Let's denote the components of C by C1, C2, blah, 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 Cn. So AC is the same thing as C1 times the vector x1 plus C2 times the vector x2 plus blah, 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 blah. Cn times the vector xn being equal to 0. Now, since the xi are linearly independent, the ci must all vanish. Because you have to recall the definition of linear independence is that whenever you have a relation like this, it implies that these coefficients, C1, C2, all the way through Cn, are all equal to 0. So we are able to conclude that C actually has to be the 0 vector, based on the definition of linear independence. So this shows that anytime you have a vector that's in the null space of A, AC is equal to 0, which implies a relation like this, which implies all the components C1 through Cn are 0. And thus, the null space of A only has one vector. namely the 0 vector. And that completes the proof of problem 7. Okay. All right. So let's go back up. That does problem 7 of homework 4. Marcus Wink asks regarding similarity and changing basis. How do we know when to do b is equal to this versus doing b is equal to this? Okay. So I'm going to try to answer Marcus's question because it's a very good one. So let's go down here and make a few new slides. Okay. So here's the setting. Suppose we have a vector space V. And 2 bases. So one base is going to be called E, and the other base is going to be called F. So this will consist of vectors v1, v2, through vn. And this right here will consist of vectors u1, u2, through un. Then associated to each basis we have spaces of coordinate vectors. Rn, and then I denote with the subscript E, and Rn I denote with the subscript F. So I just want to remind you guys real quick about how this works. We have a natural identification, or maybe I'll omit the word natural. We have an identification of Rn E with V by sending, say, a vector C1, C2, blah, 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 Cn, to the vector C1, V1, plus C1, or C2, V2, plus blah, 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 Cn, Vn. So the whole point of using bases for a vector space is that we can think of our vector space in terms of the space of coordinate vectors. In some sense, we're saying that V is the same as the set of coordinate vectors because we have this explicit identification between them. The fancy word to use is that we say they're isomorphic, but that's not a word that we really like to throw around in this course. Another reason we do it, and this is the reason it kind of comes up in chapter 4, is that if we have a linear transformation, say L from V to V, it determines matrices. And so one matrix here will correspond to the coordinate vectors associated with the basis E. So we're going to have a matrix A from Rn E to Rn E. And we're also going to have one corresponding to the basis F. And the question is, how are the bases, or how are the matrices A and B related? So here's how we can answer this. What we need to do is we need to find a map, say from Rn E to Rn F. We'll call it S. And so what we do is we need a change of basis map, or a change of basis matrix. Let me explain very briefly how S works. So suppose I have a column vector here, C1, C2, blah, 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 Cn. This is associated with something in my vector space, namely C1, V1, plus C2, V2, plus blah, 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 Cn, Vn. But I can write everything in my vector space also in terms of the vectors u1, u2, and un. So I could alternatively write this as d1, u1, plus d2, u2, plus blah, 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 dn, un. And this right here corresponds to the coordinate vector d1, d2, dn, and the change of basis matrix S is the matrix that takes vectors c1, c2 through cn to the associated vector d1, d2 through dn. So if this vector here is x and this vector here is y, then we have Sx is equal to y. That's what the change of basis matrix S does. So whenever you're doing a similarity problem, one of the things you have to figure out is you have to figure out what the change of basis matrix S is. So we go up here, and let's say we know what the matrix S is. We can draw it. It's going from Rne to Rnf, so it goes down like this. Now, here's what we can observe. If we're going over by b, because this square is commutative, It's the same thing as going up and then over and then down. So when I'm going up, I'm going in the opposite direction of S. So that corresponds to S inverse. And then I'm going over by A, such as corresponds to multiplication by the matrix A. And then I'm going down, in this case in the same direction as S. So I put an S here. But by going up, over, and down, that's the same thing as simply going over by B. So I have equality of S, A, S inverse, B. And this is how the matrices A and B are related. So Marcus asks, when do you know when to use S, A, S inverse versus S inverse, A, S? And the answer to this question is it depends. If our change of basis map was, let's say, from R and F to R and E, and so this is given by T, then we would have instead had, we would have gone up by T, across by A, and then down by T inverse, and we would have gotten that this is equal to B. So this might be slightly confusing, but I'm telling you that this and this are in fact the same. And the reason this is true is that the change of basis map T composed with the change of basis map S is simply the identity. Because we in fact have the relation that S inverse is equal to T. So depending on how you set up your problem determines whether you want to model it like this or you want to model it like this. But in the end, you get the same thing. And the reason you get the same thing is because S inverse is equal to T. Let me do a sample problem to kind of illustrate the ideas. So what I'm going to do is I'm going to look at R2. I'm going to use the standard basis. And I'm going to consider the map from R2 with the standard basis to R2, with the standard basis given by the matrix 1, 2, 1, 3. And then I'm going to come up with another basis, F, and my other basis F is going to have, say, vectors 1, 1, and 1, negative 1. And so I'm going to have the space of coordinate vectors associated with this basis. And likewise, this matrix right here is going to determine a matrix B here. And I want to compute B. So the problem is to compute B. And so the first thing I have to do is I have to figure out how to relate this space of coordinate vectors with this space of coordinate vectors. In other words, I have to go over here, back to this picture, and I have to figure out the change of basis matrix S. Well, it turns out that this is kind of really easy here because we're using the standard basis. And so changing from an arbitrary basis to the standard basis is actually really easy. So here's how. One zero in R2F corresponds to 1 1, and 0 1 in R2F corresponds to 1 negative 1. So the change of basis matrix here goes up like this. We'll call this, actually, just to be consistent with my previous notation, I'm going to call it T. And what T here does is T sends 1 0 to 1 1, and T sends 0 1 to 1 negative 1, which means T is modeled by the matrix 1 1 1 negative 1. So now I can proceed with my problem. So let's take everything I have here, move it to a different slide. And here I'm just going to replace T here with 1 1 1 negative 1 1 1 1 negative 1. Now, in order to proceed with solving this change of basis problem, I also have to compute T inverse. So T inverse here is going to be simply, let's see, so I negate this, I swap this and this, so I have one here. That doesn't work. Oh, okay. So here I should have negative 1, and then everything should be divided by 2. Now let me sanity check myself to make sure this works. If I multiply this by this, I get 0. This by this, I get 0. This by this, I get 1. This by this, I get 1. Okay. So I've correctly computed T inverse. So now I can go about computing B. So let's think about how B is related to this original matrix. This square here commutes, which means I can compute B by going up along with this matrix, and then going over by this matrix, and then going down, which means going in the opposite direction of this. This corresponds to T inverse. So this corresponds to T, this corresponds to this matrix, and now I can assemble the relation between B and this. B is going to be equal to T first, then this matrix, 1, 2, 1, 3, and then T inverse. So this is the same thing as 1/2 here, 1/2 here, 1/2 here, negative 1/2 here. And 1, 2, 1, 3 here. 1, 1, 1, negative 1 here. So now I can figure out what B is. All I do is I take these three matrices and I multiply them together. I'll assume you guys all know how to multiply matrices and can finish up this example for yourself if you so wished. But this illustrates the basic way that you set up a similarity problem. Okay, so that, I hope, answers Marcus's question. Benjamin asks, can I go over number 3 of the picture I put in help chat on Discord? Okay, so Discord seems to be frozen right now. Alright, so while I wait for Discord to never mind. I'll do Derek's question after. Let me do this first. Alright, so everyone can hear me, right? Just double checking again before I start. Alright, then let me pick up with the last question that I was about to answer before my computer crashed. So we're going to look at problem 3 here, and these were kind of the optional problems that I posted in the Discord. So I think A here of 3 is a fun problem. Okay. So here's the question. Let S be the subspace of R3 spanned by the vectors x1, x2, x3, transpose, and Y equals Y1, Y2, Y3 transpose. What we're going to do is we're going to let A be this matrix. And what we want to do is we want to show that the orthogonal complement of S is equal to the null space of A. So I actually kind of proved this in class, or at least I proved a much more general version of it. But I'm going to go over it again right now. So here is what you can observe. Suppose X is in the null space of A, where A is this matrix. In fact, let me choose a different letter for this. I'm going to say Z. So Z is going to have components, Z1, Z2, Z3. Then this means that A times Z is equal to x1, Z1, plus x2, Z2, plus x3, Z3. And then down here I'm going to have y1, Z1, plus y2, Z2, plus y3, Z3. And this is going to be equal to the vector 0, 0. But note that if this right here is equal to 0, well, this right here is in fact the same thing as the vector x transpose multiplied with the vector z. Whereas this right here is the same thing as the vector y transpose multiplied with the vector z. So this has to be 0, and this has to be 0. And what we also know is that S is spanned by x and y. So if V is any linear combination, say C1x plus C2y, then V transpose times Z is equal to 0. Just because we know that Z is orthogonal to x and Z is orthogonal to y, so Z is thus orthogonal to their linear combination. And this means that Z is orthogonal to S. So this shows that the null space of A is contained in the complement of S. Now we also know another fact. So one fact is that the dimension of the null space of A is 1. Actually, that's not necessarily true. So, how should I phrase this? I could just prove it by appealing to theorems that I proved. Okay. I'm going to proceed like that then. So I want to prove that the null space of A is equal to this. I've proved containment in one direction, but I can prove the rest by appealing to some fairly general results. The result I'm going to use is that the null space of A is equal to the orthogonal complement of the row space of A, the column space of A transpose. But the column space of A transpose is simply equal to the span of the vectors x1, actually, I'll just call them x and y, like the problem does, And the span of x and y is, of course, simply the set S as defined in this problem. So, in fact, by general results that I proved in class, this right here is equal to the orthogonal complement of S. I was trying to do a somewhat simpler argument. And you can do a somewhat simpler argument directly if you know that x and y are linearly independent. So let me just state why this argument would be a little bit simpler if x and y are linearly independent. So if x and y are linearly independent, then what you know is that you know that the dimension of S is equal to 2. You also know that the dimension of S plus the dimension of the orthogonal complement of S is equal to 3. That would imply that the dimension of the orthogonal complement of S is equal to 1. But the dimension of the null space would also be equal to 1. And so by using the fact that we proved from scratch on the previous slide, namely that the null space is contained in the orthogonal complement, if we knew that they have the same dimension, then it in fact follows immediately that they have to be the same. So under the additional assumption of linear independence, the proof becomes a little bit easier. If you don't make that an extra assumption, you can proceed as I did down here and prove it by general theorems, namely by appealing to this relation. Okay, so Max asked if I can go over problem 8 in homework 5. So let me do that. So this is kind of a long problem, so I'm not going to do all of it, but I'll do a chunk. All right, so we have two bases, E and F, and we know what these basis vectors look like. And so what we want to know is we want to know how to represent linear transformations L from R3 into R2 by matrices in terms of the ordered bases E and F. So here's the setting. First off, let's start with A. In the standard basis, A or L may be represented by the matrix A and here's what it needs to do. So it would take if I multiplied it through by x1, x2, and x3, then I'm going to get x3 in the first component. So I'm going to have a 0, 0, 1 here. And then I'm going to get x1 in the second component, which means I have to have a 1 here and a 0 here. So let's call this A. A represents L in the standard basis. So let's look at our picture, or rather our diagram. Here I'm going to have coordinate vectors in the basis E, and here I'm going to have coordinate vectors in the basis F. This is going to be R3E and R2F. And then down here I'm going to have R3 in the standard basis. I'm going to have R2 in the standard basis. And I have my map A. Do I want to solve it this way? Or? You could solve it almost in an analogous way to this way you would solve similarity problems, which is you could put the matrix here, you could put the matrix A here, and you could try to find change of basis maps. You'd have to find a change of basis map S from the standard basis to the E basis. You'd have to find a change of basis map T from R2 with the standard basis to R2 with the basis F, call that T. And then you could go about relating A to B via S and T. But that's actually somewhat a long-winded way of doing it, and it would take me a while to set it up. So what I'm going to try to do is I'm going to try to do something simpler. But in order to do something simpler, and this is, I believe, how the book did it when I was teaching it, I need to write down how I would switch from R2 with the basis F to R2 with the standard basis. So call this S, or actually call it B. So this is actually fairly easy because B here is simply going to be, well, you take this, you make it the first column vector, 1, negative 1. You take this, you make this the second column vector, 2, negative 1. And then you figure out what B inverse has to be. So B inverse here, so this ends up being, let me think for a second. I believe this becomes negative 1, this becomes positive 1. And this becomes 1. And this becomes negative 2. Let me double check, make sure that works. I believe it does. Okay, so I have B inverse. So let me explain how I can use B inverse here to solve the problem of expressing L in terms of the basis E and F. So here's what I can do. I can compute L of U1, U2, and U3. So this is actually very easy to compute these. But not only do I have to compute them, I have to actually express the answers as C1, 1 times B1 plus C1, 2 times B2. Maybe I don't want to put those in the exponents because they get confused with powers. So I'll write it like this. And then I also have to compute L of U2 in terms of the vectors B1 and B2. So this would be 1, 2, B1 plus C2, 2, B2. I do the same down here, C1, 3, B1 plus C2, 3, B2. So the problem of expressing this linear transformation in terms of these bases amounts to finding these numbers. But there is something we can do. So if we compute LU1, LU2, and LU3, then what we actually get is we get the vector C11, C21 is equal to B inverse times L of U1, C12, C22 is equal to B inverse L of U2, and C13, C23 is equal to B inverse of L of U3. And if we have this, this, and this, then the matrix representing L is just C11, C21, C12, C22, C13, C23. So the problem of representing our matrix with respect to these two bases just amounts to finding these numbers C. And this right here gives us an explicit recipe to go about finding them. So this is one of the theorems in the book, just to show you guys which one it is. Let me open it up for a second. And I believe it's the chapter right before similarity. Maybe it was the one before that. Here, it's this result. Theorem 4.23. So that's what I'm using here. And now what I have to actually do is go about computing all the things. So first thing I'm going to note is that L of U1 is the same thing as A times U1. So this is 0, 0, 1, 1, 0, 0, and then multiplied through by 1, 0, negative 1. And so this right here is simply negative 1, positive 1. And now what I can do is I can take this and I can apply B inverse to it. So I can take B inverse of negative 1, 1. So this is the same thing as negative 1, negative 2, 1, 1, multiplied by negative 1, 1. And this right here is simply negative 1, 0. So this gives me C11 and C12. So now I know what the first column of my matrix is. Let's do the second column. L of U2 is equal to A of U2. So 0, 0, 1, 1, 0, 0, multiplied by 1, 2, 1. And so this is just 1, 1. And so now I have to take 1, 1, and I have to multiply it by B inverse. And so this is the same thing as negative 1, negative 2, 1, 1, multiply through by 1, 1, which is just, let's see, negative 3, positive 2. And so this gives me C22, or actually C12 and C22. And then finally, I have to compute L of U3. And this is going to be 0, 0, 1, 1, 0, 0, multiplied through by negative 1, 1, 1. And so this will give me 1, negative 1. So I go back over here and I multiply this by B inverse. This is the same thing as negative 1, negative 2, 1, 1, multiplied by 1, negative 1, which gives me positive 1 here and 0 here. And so this gives me C13 and C23. So finally, I can conclude that the matrix representing L in the bases E and F is negative 1, 0, negative 3, 2, and 1, 0. And this completes the computation of part A of problem 8. Okay, so I'm going to do another example from this problem because it seems that that's popular demand. So I'm going to do part B of problem 8. So as before, the first thing I'm going to do is I'm going to, step 1, is to represent L in the standard basis. So if I do that, I'm going to get a matrix A. And the first entry is x1 plus x2, which means I'm going to have a 1 here and a 1 here, a 0 here. For the second row, well, I'm getting x1 minus x3, so I'm going to have a 1 here, a 0 here, and a negative 1 here. So this completes step 1 of the problem. Now I'm going to use the same facts that I used last time, namely that I can figure out the columns of the desired matrix C by computing L of UI and then multiplied through by B inverse. Now, fortunately, this is actually the same B inverse we computed earlier, so nothing changes, because we're still using the same basis B. So I can bring that down here. So now what we can do is we can go through this problem. First thing we'll do is we'll compute L of U1. This is the same thing as 1, 1, 0, 1, 0, negative 1, multiplied through by the vector 1, 0, negative 1, which is 1 here, 2 here. So I take the 1, 2, and then I multiply it through by the matrix negative 1, negative 2, 1, 1. And what do I get? I get negative 5 in the first component and 3 in the second component. Next thing I do is I compute L of U2. And so this is the matrix 1, 1, 0, 1, 0, negative 1, multiplied through by 1, 2, 1, which is just going to be 3 here, 0 here. So I take that, I multiply it by the matrix B inverse. So negative 1, negative 2, 1, 1. And this is just going to be negative 3, positive 3. And then finally I compute L of U3. So this will be 1, 1, 0, 1, 0, negative 1, times negative 1, 1. So this will be 0 in the first component, negative 2 in the second component. So I'm going to take that, and I'm going to multiply it by the matrix B inverse. So negative 1, negative 2, 1, 1. And this just ends up being positive 4, negative 2. So now I have all the data needed to assemble my matrix. The matrix C, representing our linear transformation in the desired basis, is negative 5, 3, negative 3, 3, and 4, negative 2. So that completes part B for problem 8. Ultimate calculator asks to determine if this is a subspace. Okay, so let me write down the problem. Determine if S, which is going to be the set of vectors, x1, x2, x3, with x1 plus x3 is equal to 1 is a subspace. So here's what we know. If S was a subspace, and x and y are elements of S, then x plus y is also an element of S. However, that is not true for this specific S, because, well, suppose we have x1, x2, x3, we know that x1 plus x3 is equal to 1. And if we have y1, y2, and y3, then we know that y1 plus y3 is equal to 1. Now suppose we add this vector to this vector. Then we get x1 plus y1, x2 plus y2, and x3 plus y3. But then, if we add the first component to the third component, we have x1 plus y1 plus x3 plus y3. Well, this is not actually going to be equal to 1, it's going to be equal to the sum of this relation with this relation, so it's going to be equal to 2. So if you take two vectors in S and you add them together, then you get something that is no longer in S. So, consequently, S is not a subspace. So to answer the last question, let me see. Marcus, I'm referring to these 3 problems. If you want, you can find them in the Discord chat. Alright, so Derek asks, can I explain the null space and linear independence in simple terms? So let me see. Where did I put my pen? Here it is. Okay. So I'm going to go over these real quick. So I'm going to start by doing an example. Suppose I look at the vectors v1, so this is going to be the vector 1, 1, and the vector v2, which will have components 2, 2. Then you'll notice that there's a relation between this vector and this vector, namely that 2 times v1 minus v2 is equal to the 0 vector. So we have a relation between the vectors, and the relation tells us that if we form some combination of them, some linear combination, we get the 0 vector. So we say that a set of vectors is linearly independent if there is no non-trivial way of expressing the 0 vector as a linear combination of them. So this is how I would explain what linear independence is. The way I think of it in my head is, if I have vectors, can I find some coefficients that are not all 0, such that when I form a combination of those vectors with those coefficients, I get the 0 vector? If I can, then the vectors are not linearly independent. But if I can't, then they are linearly independent. Does that work, Derek, for linear independence? For the null space, the null space of A is just the set of all vectors x with ax is equal to 0. So any vector such that when you apply the matrix x to it, you get 0. Now, in fact, the null space is a special manifestation of something that's called the kernel. So if L is a linear transformation, say L goes from a vector space V to a vector space W, then the kernel of L is the set of all vectors V, little v and big V, with L of V is equal to 0. So this is the kernel, and it's very closely related to the null space. In fact, in a certain sense, they are the same concept for finite dimensional vector spaces. When you're working with infinite dimensional vector spaces, the notion of kernel still makes sense. But the notion of null space doesn't really make sense because you don't really talk about infinite dimensional matrices, at least not usually. So these are the notions of null space and kernel. All right. So I'm gonna wrap this up for tonight. Does anyone have any final questions they want to ask? So if not, I wish you all good luck on the exam tomorrow. And yeah. So I'll see you in the morning. Good luck.